All right, thank you very much for the introduction, and also a big thanks to the organizers for inviting me here to talk about my work. So this work is mostly picking up where Sebastian stopped this morning, and it's been performed mostly by myself under supervision of Professor Bart van Wees in Groningen. And now we have some more people working on this, so Jing Liu and James Shan, PhD students in our group. Timo Kuschel is now a postdoc. And we have theoretical support from Gerrit Bauer, Rembert Duyne, and also Kevin Peters from Rembert Duyne's group. And some of our samples are supplied by Jamal Ben Youssef from the University of Brest. Okay, so before I move on to the real stuff, I just want to pause for a minute at the concept of Magnon Spintronics, which was introduced yesterday by Burkhard Hillebrands and Alexander Serga. And I think there are kind of two approaches to doing Magnon Spintronics. And the approach that has been taken by the Kaiserslautern group is to excite magnons using microwave photons. And that gives you very selective excitation. So you excite magnons at gigahertz frequencies. And there's, of course, this review by André Čumak and colleagues, very detailed, giving a very detailed overview of the progress in this field. So we in Groningen take a bit of a different approach, as well, Sebastian also showed this morning. So we just take, in a sense, the most basic tool that we know from spintronics, which is a pure spin current, and we use that to excite the magnetization dynamics. So thereby combining spintronics and magnonics into Magnon Spintronics. But in doing so, we lose the frequency selection that they have in Kaiserslautern, but our excitation process becomes a bit easier. You can essentially just use a DC current source instead of a microwave source. So that's the trade-off you have there. And I think the two approaches are very nicely complementary, actually. So the way we do our excitation, this has also been highlighted this morning, is by using spin flip scattering. So we have a bilayer stack like this. We have yttrium iron garnet and some heavy metal where a spin Hall effect is present. We create a spin current in the metal towards the yttrium iron garnet interface. At the interface, the electrons cannot enter, and upon backscattering, there is a finite probability that an electron will flip its spin. And the difference in spin between up and down is transferred as, into the YIG as a magnon. Now, the reciprocal process can also happen. So magnon absorption will also take place, thereby, as was also highlighted this morning, absorbing spin angular momentum from the magnet. Now, the nice thing about this is that it's very localized, so it only happens at the metal YIG interface, where the spin accumulation that you build up here generates a magnon accumulation in the magnet, and it's also fully linear. Both of these processes are fully linear, so you can work in linear response. And so that gave us the idea to do the non-local experiment that also Sebastian discussed. So we have a platinum injector, platinum detector strip. We use this. We pass a charge current through the injector strip using spin Hall effect to generate a spin current, which couples to the magnetization in the YIG, generating magnons. And here we use the inverse spin Hall effect to detect. Now, I have to say that we don't use a purely DC current. You could do that actually in Sebastian group. That's how it's done. But we use AC current with a very low frequency, typically 10 Hertz or so, so that we can do lock-in detection on this detector strip. So we can separate contributions that are proportional to the first harmonic, so the frequency we inject the current, and the second harmonic, so double the frequency that we inject the current. And in this way, it turns out that you can separate effects that are linear in the current and that are quadratic in the current. And this will, later in my talk, I'll show why this is important. It's a very nice tool, I think, to do these kind of measurements. So and then in the linear regime, so when for the first harmonic response, we define a non-local resistance just like this. So the voltage we measure over the current we send. So these are some optical image of our device. We have devices exploring two distance regimes to map out clearly the distance dependence of the Magnon spin signal. So for long distances, we use very long platinum strips, and for short distances, down to 200 nanometers, we make them a bit shorter just for technical reasons. Lithography becomes easier when you do it like this. And then we pass a current in the injector strip and we measure the voltage over the detectors. And thereby, we change the angle between the magnetic field and the sort of transverse direction of the strip. So just the same as shown by Sebastian, actually. So what you find for the first harmonic response signal as a function of angle, that looks like this. So here you see angle versus the non-local resistance here on the y-axis. And you get this cosine square dependence. And the way this cosine square dependence comes about is illustrated in this schematic. So here you see our device, the top view of the device. We have the injector and the detector. We pass the current here, which generates by the spin Hall effect, generates a spin accumulation mu I. But because of the way we can inject magnons, we are only sensitive to the projection of mu I on the YIG magnetization. So that is here mu parallel. Now that gives you your first cosine alpha dependence. And in the detector, when the magnons are generated here, they diffuse to the detector, and there they generate a spin accumulation, mu parallel, so parallel to the YIG magnetization. But because of the way we detect, we can only detect the component of mu that is really transverse to our voltage measurement direction. So we only are sensitive to mu d here, and that gives the second cosine alpha, resulting in a cosine square alpha, because the signal is a product of injector and detector processes. So then, as I said, we want to vary the distance between injector and detector to see how the signal decays as a function of distance. And this is what we get. So here I plot the distance in microns and the non-local resistance. And this is really the amplitude of the oscillation. So we do these angle-dependent measurements for at a lot of distances, and we look how the amplitude of the signal changes. And well, then you see we get something like this. And we initially described this by a very simple 1D model for spin transport. So we just used the very familiar 1D spin diffusion equation, where Nm is the non-equilibrium magnon density that we inject. So those are the magnons we inject into the magnet, and lambda is the spin diffusion length for those magnons, which is the characteristic length scale over which they decay. And then we apply the boundary conditions set by the platinum contacts, and we find this expression for the non-local resistance, which is then here used to fit the data. So you see the dashed line describes our experimental data pretty good. And you also see that there are two regimes in the signal decay. So we see for very long distances, this is a straight line on a log scale, so it's pure exponential decay. And from the slope of this curve, you can actually find the spin diffusion length. Turns out to be roughly 9.5 microns. And when you go to distances that are actually shorter than the spin diffusion length, you can imagine that relaxation of the magnons is not so important yet. It's not the dominant decay mechanism. And there you enter the diffusive regime, where basically the magnon transport just drops off as 1 over the distance d. So just purely by moving the detector further away, the total spin resistance of the channel becomes larger. That's where this 1/d decay comes from. So, well, that's our very simple description that we used initially. And then we were wondering, okay, if we want to make a bit more rigorous description, how can we go about it? Can't we just use the model for interfacial spin-Seebeck effect that was developed then by Xiao and colleagues in 2010? So then that would mean that in the injector you generate some temperature difference between the electrons in the metal and the magnons in the YIG. And at the detector, so that's what you could call the interfacial spin-Peltier effect. And at the detector, you would use the reciprocal effect, so the interfacial spin-Seebeck effect, to detect the signal. And turns out that this actually does not work, but you only see it when you really plug in a number. So you see that the thermal conductivity of the magnons is really several orders of magnitude too small, and the magnon phonon relaxation length is also way too small to be able to explain the signals that we observe. So in this recent paper, we described the details of this calculation. So then we figured, okay, we need some other way to describe the magnon system. We cannot just describe it using a magnon temperature and spin-Peltier, spin-Seebeck effect. So we introduced the magnon chemical potential as one of the out of equilibrium parameters to describe the system. So now there's also a kind of intuitive reason to do this, because you can imagine processes that conserve magnon number but do not conserve magnon energy. So of course you can only have a non-zero chemical potential when your magnon number is conserved. And magnon number conservation, the time scale of that is set only by magnon relaxation, so processes which make a magnon disappear. But on the other hand, the energy of the magnon, so the temperature difference with respect to the lattice, you could say, that is of course also affected by these processes that cause magnon relaxation. But you can also imagine magnon phonon scattering, so magnon coming in, scattering with a phonon, giving its energy to the lattice, but still the magnon itself persists, and that conserves spin, and also conserves the number of magnons, but it does not conserve energy in the magnon system. So hence you can argue that this magnon temperature will relax quicker to the lattice temperature than this magnon chemical potential. So if you take then a normal metal magnetic insulator interface, then the picture can look like this. So you can bias it with a temperature gradient, and then at this interface there will be some length scale over which the electron temperature is different from the phonon temperature, and also the magnon temperature here is different from the phonon temperature over some length scale L and P. But this length scale will typically be shorter than the out of equilibrium length scale for the chemical potential. So if we send the spin current by the spin Hall effect into the magnet, this will generate a spin accumulation in the metal, which will induce magnon accumulation in the ferromagnetic insulator. And this magnon accumulation can relax on a much longer length scale than the magnon temperature. And then if you write down the linear transport theory, this is what you get. So this is the Onsager matrix with the magnon spin conductivity and the magnon thermal conductivity. And of course we have the spin-Seebeck and spin-Peltier terms, but these are now the bulk spin-Seebeck and bulk spin-Peltier coefficients. And it turns out that for the first harmonic signal, actually the only thing that you need is really these three terms, so just the spin conductivity and the gradient of the chemical potential. So you can, we we took those terms and we built a finite element model of our device. So that I show here, it's a 2D finite element model. Here we have in the middle the injector, and the color plot encodes the chemical potential of the magnons. And you see at the injector there's a maximum mu, which then diffuses away to the detectors. And I should mention that the spin current that is injected in the magnet is proportional to the difference in chemical potential between magnons and spins at the interface, and then times this constant Gs, which relates to the mixing conductance. So it's not exactly the same. It's an effective mixing conductance, because the mixing conductance is valid for when the spin accumulation and magnetization are perpendicular to each other. And here we're talking about the collinear case. So that's why this is not exactly the same as the familiar mixing conductance, but it's some effective mixing conductance. So, well, here I plot a line cut, so you see the injector maximum, and you see that the detector, they take some spin out of the system, but it doesn't drop all the way to zero. There's still finite chemical potential that persists, and that is, as Sebastian indicated, because the spin sinking efficiency of the platinum is not infinite, so there's some finite transparency at this interface that prevents all the magnons from being absorbed. So part of them are just not absorbed by the detectors. So this model gives a good agreement with the experiments, at least for this electrical generation. And we can find then, of course, the parameters that govern the transport, so the Magnon spin conductivity and the effective mixing conductance. However, I should say that we recently started doing also these experiments as a function of YIG thickness, and there it goes a bit awry, so we're not sure yet how to interpret those experiments completely. So I have a slide on this in the end, which I will show if I have time. I see a question there.
How do you calculate the chemical potential for the magnons?
Right, so that's you can calculate the chemical potential for the spins in the metal at the interface, and then the Magnon chemical potential just follows from the magnitude of Gs, basically. So they're directly related. You only need to know what Gs is. And Gs we know that it cannot exceed the mixing conductance, but it should be some small fraction of that, because otherwise, if it would, it cannot be larger than the mixing conductance itself, but must be some percent or so. And then we just do a fit to extract this value itself. Right, so then what we can do is see how temperature changes things. So we can do a temperature dependence, and again look at the first harmonic signal for different distances. So here I only show 3 distances for 3.5 microns to 10 microns. And well, this picture, or this kind of experiment was also done by other groups, of course. So it agrees, what we find agrees with their findings. And now we can actually use the distance dependence and our finite element model to find the temperature dependence of these these transport parameters that govern the Magnon transport in the magnet. Right, so this is what we find for the spin diffusion length here, and for the Magnon spin conductivity over here. And especially this one, it's a bit controversial. You see it does not do so much. And other groups using other methods to extract this, or the relevant length scale for the Magnon transport, they find different things. So yeah, I'm not sure how to interpret this, but this is what we see for our YIG samples. So not going to say too much about it otherwise. And then now we can, so that concludes my topic of the electrical Magnon generation. And now I want to move on, because from this matrix you can indeed expect also some thermal Magnon generation. So the temperature gradient can also drive a Magnon spin current via this bulk spin-Seebeck effect. So Joule heating in our devices will also cause a Magnon accumulation in the device. So here's the picture for the electrical case, where I show the injector and the chemical potential profile in the magnet. And for the thermal case, so when you take into account the Joule heating in the injector, you can find the profile of the temperature in the YIG, and from that you can deduce the chemical potential profile for the magnons. So you find something like this, where the color encodes again chemical potential. And you might ask, okay, what is the difference between the two? It looks similar. Here we have some chemical potential profile, and here as well. But what is really quite crucially different for the thermal case is that there's a heat current flowing away from the injector, and the heat current can flow out via the GGG, so it can leak away to the substrate, if you will. Of course, the Magnon spin current cannot, so that is confined in the YIG channel, and that causes really different physics for electrical to thermal case. So you see the most striking feature, I think, is that this chemical potential actually reverses its sign from close to the injector to farther away from the injector. And this will become important in a minute. So for the thermal generation, here is what we do. We again use our same geometry, but now instead of the linear signal, we look at the second harmonic response. So that is proportional to the current squared. And of course, the current squared also generates a temperature gradient in the device. So by spin-Seebeck effect, this also generates a Magnon current in the device. And so the angle dependence of the second harmonic response look like this. So you have here your angle and the second harmonic non-local resistance. And you see we're now left with a pure cosine alpha dependence. And the reason is, of course, that the heat we generate here is constant with angle. So the heat in the injector generates a Magnon current, which we pick up at the detector, where the detection process is exactly the same as for the first harmonic case. So we are only left with a pure cosine alpha dependence. Now, if we look how this signal decays as a function of distance and compare it with the first harmonic, then we see that they're actually very similar. So this is what we find for the first harmonic, for the second harmonic, and also the spin diffusion lengths that we extract for both cases are very similar, at least within our experimental accuracy, we don't see any difference. So how do we model this? I already briefly mentioned it. So just go through it once more. There's a heat current resulting from Joule heating in the injector that flows outward. So that's indicated by these red arrows. This, by the spin-Seebeck effect, generates a Magnon current. The Magnon current cannot enter the GGG interface, so magnons will accumulate, if you will, at this interface. But by diffusion, they also spread out again into the YIG. And this is what causes this sign reversal here. Now, you might wonder, do you also then see this sign reversal? Actually, yes, we do. But we have to zoom in a bit. So if we focus on the short distance regime, for the first harmonic, what we see in the short distance regime is really a purely 1/d dependence that indicates this diffusive transport that I outlined before. But for the second harmonic, what we see is something different. We see a peak in signal, and then at very short distances, the signal indeed changes sign. And it turns out that this sign change, like the exact location of the sign change, also depends on YIG thickness. So you can, by increasing the YIG thickness, this sign change also shifts to larger distances. So it's really there and it's really reproducible as well. So the injector for the second harmonic for thermal Magnon generation is not a localized source for Magnons, but it's a bit more complicated than that. And also, what is, I think, quite interesting is that the temperature dependence of these two effects is really completely different. So this is the temperature dependence I showed already for the first harmonic. And for the second harmonic, we find really completely different behavior. So we find a peak at about 6-7 Kelvin, where it's really an order of magnitude enhanced compared to the room temperature signal. And this, well, I have to just be frank, we don't understand why this enhancement is there. So it's just a kind of fact. I put it out here now. Right, so to summarize, I showed you that we can use these kind of devices to convert between charge, electronic spin, and magnonic spin currents. And we can use either electrical Magnon injection or thermal Magnon injection, which you can very clearly distinguish by their current dependence and their angular dependence. I've also showed that YIG is a good conductor for also diffuse spin currents, so not only the coherent phenomena that we talked about yesterday, with a long spin diffusion length of about 9.5 microns. And that the Magnon chemical potential is really an essential parameter in describing the Magnon transport in these YIG films. So also, I showed that the temperature dependence for electrical and thermal injections are completely different, but the spin diffusion lengths agree. And actually, I didn't show that yet, but I'll show it now. So this is again the graph for the spin diffusion length, and we have extracted it from the first harmonic and the second harmonic. So that are the red and blue data points that you see. And you see that what we find agrees over the temperature range that we measured. So with that, I'd like to thank you all for your attention.